In this class, we study statics and elasticity. Statics is very important to build a building or a structure. If your bridge is unstable, it is very dangerous, and all lives are very important. So statics in human history, in physics, actually began with statics. We should build a building in which we live. Until now, we have studied dynamics, Newtonian dynamics, and we have solved many equations, constructed the equation motions for the linear version and rotational version. And we were trained to solve the equations of motion. However, in the statics, the equations are quite simple because F equals ma. In statics, we study static equilibrium. That means it does not accept any force. The net force must vanish. In addition, net torque, X cross F, sure, it should be some sum of all of the torques applied to rigid body that must vanish too. So quite simple in comparison with dynamics problem. If you look at the equation more closely, these are vector equations. So force equation have three components, three Cartesian components, and the torque equation has three Cartesian components. Therefore, in naturally, E equals 0 means F1 net equals 0, F2 net equals 0, F3 net equals 0, and tau 1 net equals 0, tau 2 net equals 0, tau 3 equals 0. Therefore, we have 6 linear equations. A system of linear equations. Therefore, we need to develop a way to solve these linear equations because the left-hand side is a sum of forces and they are added in linear form. X component of force is, for example, we have three forces. We have to sum F1, F2, F3, and that's X component, Y component, X component, and Y component, and Z component separately, and the sum of them must vanish. So as far as the number of variables concerned, we have many variables. So intrinsically, we have to solve the linear equations. In mathematics textbook, we learn that a kind of a way of solving the linear equation is the Cramer's rule. Let me briefly review what Cramer's rule is and how to solve the linear equations. In the case of torque is net torque is a sum of torques and tau I, that is the ith component. If there are n forces applied, then there is a axis of rotation. Usually we choose the center of mass, but in equilibrium it doesn't matter. For simplicity, we have chosen the center of mass and have chosen the axis of rotation. And then consider these forces. In general, these forces are distributed in 3 dimensions, but for simplicity, we have restricted in the 2-dimensional case. Although the forces are on a 2-dimensional plane, the torque is always normal to that plane. So we have this axis. Sure, in general, we have to consider all 3 axes to find out the net torque for this axis, net for this E3, for example, E1 and E3. All torques must vanish. Let us consider the general case of rigid bodies in here and assume that we have a center of mass at this point. It looks asymmetric. Perhaps the density on the left-hand side is greater than the density of the right-hand side. Anyway, the center of mass, at the center of mass, the gravitational force is applied effectively. That means actually every part has its own mass, and we have MIG, and we have to sum everything all together to find the total net force applied to this rigid body. We have to sum this, but because G is constant, we have to pull this one out, and G is out, and mass can be integrated simply. So total mass times G is the net force. But the point, the effective point at which the gravitational force applies is at the center of mass. Because assume that we have the gravitational force on the right side, and mg is applied in here. Because there is a cm, and we have the lever arm, we have a torque, then it is not in equilibrium. Instead, it is rotating in this way. If it is placed on the left side, then the force is downward, and there's a lever arm from the center of mass to there. In that case, torque is applied this way, counterclockwise. So in either case, the torque is applied. As soon as the torque is applied, the rigid body is not in equilibrium at all. So to have it in equilibrium, we have to choose the center of mass. Sure, it is possible to have them all along the vertical line that is passing the center of mass. That's fine. However, center of mass is correct. Let's see. Let's compute the torque relative to the center of an axis that is passing through the center of mass. Then we can compute the relative lever r. This is x bar, relative displacement from CM to a point where differential mass is placed. Again, we have G that is constant. Cross G is factored out. We can pull this one inside. And x bar dm, what is it? What is it? This is particles position subtracted by the center of mass. And we integrate over the mass. What we obtain is this xi vector dm is the total mass times the center of mass. And the second term, center of mass is factored out, and we can integrate over the mass. That is, again, m times xcm. Same thing, subtracted. So zero cross gravitational acceleration means a zero vector. But that's the reason why that the torque disappears if we choose the axis that is passing through the center of mass. So that's the reason why in equilibrium cent- the gravitational force is applied at the center of mass. When it solves a linear equation, I already told you the finding the relation for the equilibrium involves solving 6 linear equations, and 3 of them are for the three Cartesian components of the force, and the other 3 is for the 3 Cartesian components for the torque. Let us consider this equation. We have 1, 2, n variables, and we have n coefficients. If you ask Descartes, and Descartes tells you, this is a scalar product of 2 vectors defined in an n-dimensional Euclidean space. As long as you have introduced a unit Cartesian basis vector, EI, hat, that where I runs from 1 to n, and just introduce the scalar product of EI dot and EJ dot is a canonical delta that is either 1 or 0. If it is 1, that means I equals j, and if I is not equals to j, then it is vanishing. Okay, so this seems to be a coefficients, and actually Cartesian components of n-dimensional vector. And these are the Cartesian components of n-dimensional vector x. And these are this is a scalar product between them. The left one is written in a row vector, and right one is written in a column vector. And the answer is magnitude of A, magnitude of B, and cosine theta between them. I don't know how to draw the figure in this n-dimensional case, but anyway, this one should be between these two. So that's fine to introduce a cosine theta, because cosine theta ranges from -1 to 1. That's fine. Anyway, this one can be expressed as a scalar product. That's quite important. So what about solving linear equations? We have n variables, unknowns, and there are coefficients. That means we have a a1 vector, a2 vector, and an vector. And their scalar product with x is b1, b2, and bn. Aha, this one means an n linear equation. I have n unknown variables, and every line is a linear combination of x, and their coefficients are treated to be the n-dimensional Cartesian vector, a Euclidean vector, and these numbers are Cartesian components. I mean, a vector is a1, e1 hat, and an, en hat, something like that. All right, that's fine. Then these numbers, that is 1, 1, 1, 2, 1n, and 2, 1, 2n, and n1, and n, multiplied by x1 to xn equals b1, b2, and bn. Okay, I'd like to solve this equation. And let me call this matrix A, and this is a matrix X and matrix B. This is an n by n matrix, n by n square matrix. Square means number of rows and number of columns are the same. And this is a n-dimensional column matrix. And this one is again the n-dimensional column matrix. All right. So I have a problem. What problem? To solve AX equals B. What I want to do is I multiply inverse matrix. Inverse matrix. Something like that. And I claim inverse is identity. Inverse and this matrix product is identity. How? I don't know yet. But if I find this one, identity matrix is 1, 1, 1, 1. If I multiply 1, 1, 1 and everything else is 0, x1 to x2, if I multiply, the answer is x1 to xn, identical result. Aha. Then the left-hand side becomes just x. Oh, what's x? X is A inverse multiplied B. That's it. That's the answer. Then how can I find an inverse matrix? That's the problem. The answer is given the later part of this lecture. Determinant. In order to find out the solution, we have to find out the determinant. What is the determinant? Determinant is, for example, if determinant A equals 0, for simplest case, we consider this 2 by 2 matrix. This one is for the linear equation ax by equals something, and the cx plus dy equals something. The middle school student can solve this problem. First, they will find the slope of the two straight lines. They want to compare the slope. This slope is if b is not equal to 0, the slope is y equals minus a over b x something. Slope is a over minus a over b. This one is a minus a c over d. So we want to compare this slope because when the slopes are the same, they can never be either. This is case one. They are identical, case two. Case three is the slopes are different and they meet at a single point, and there is the answer. And these are two cases are too simple, so we can separate it out. And what we want to do is we would like to find this kind of form in physical problem. There is no stupid question. Actually, these are stupid questions. We don't have to write the problem because identical case, these two equations are identical. We do not have such a redundant equation at all because physical system has exactly a single solution that has some equilibrium. So what we want to do is we do not want to find this unphysical system. What we want to do is to solve the linear equation that has a unique solution. Okay, what's that? The slopes are different. Slopes are different. This is slopes are the same. What's that? AD equals BC. AD minus BC equals 0 is the slopes are the same. So AD minus BC is not equals to 0. Those two lines have different slope. So they cross at a single point. Aha, determinant is to find whether the slope of the two lines are equal or not. And if they are equal, problem becomes trivial and that is not physical. And if they have some crossing point, then the two slopes must be different. Let us further think about the case because we have introduced a vector. I told you these are two Cartesian components of a single vector. For example, A, capital A, and Cartesian component of a single vector B, right? What is AD minus BC? AD minus BC, A, E1, B, E2, B vector, C, E1, D, E2. How can I find the AD minus BC? AD minus BC. Aha! A cross B. A cross B. A cross B. AD E1 cross E2 plus BC E2 cross E1. Permutation gives it is a negative sign. It is AD minus BC unit vector E3 hat. Aha! Determinant is nothing but a cross product, third component of cross product. That means because these two rows represent two vectors, if they are not parallel, they can construct a parallelogram, and the area of the parallelogram is proportional to the A cross B. Haha. Determinant says if there are two vectors are linearly independent to make a non-vanishing area made of a parallelogram spanned by these two vectors. That's it. What about the case of a three-dimensional one? Three-dimensional one, we have three vectors. And I already told you these three vectors gives a determinant of these three vectors gives the triple scalar product. And I have repeatedly told that this triple scalar product is the volume of a parallel pipe generated by these three, A1, A2, and A3. These three vectors, this is volume. So the determinant is not vanishing only if the three vectors are linearly independent to make a non-vanishing volume. That is the requirement of having unique solution for the three equations, a system of three linear equations. In such a manner, we can extend the n by n matrix. Then we need to find if there is a unique solution. Every row is linearly independent of any other rows. Only if it is the case, the volume is non-zero. And as soon as the volume is well defined, then the inverse exists. Only if inverse exists, there is a solution for x unknown variables that becomes a unique solution. And we have repeatedly trained how to expand the determinant. So let me pass that part. Let me quote how to use the Cramer's rule to solve the linear equations. This is not making use of inverse matrix. Instead, it is just using determinant only. Simple trick is that we know how to compute this determinant. This one is in here in the denominator, the volume of the parallel pipe generated by ABC. And answer X is to choose the numbers that is to be multiplied to X. That is this first column. And replace this first column with the right hand side. Substitute and take the determinant. And Y, replace this second column with this PQR in here. The Z, these numbers that is to be multiplied to Z, replaced with the PQR. Why? The answer is given in usual mathematics textbook. And this is the way how mathematicians used to solve the linear equations. In addition, there is another. But at the end of this lecture, we have a self-test part, and there is a way of solving linear equation in a physicist way. The mathematical way is compact, right? But you will find that physicist way is a much more compact. And mathematical way looks elegant, but it is very difficult to remember. That's the problem. They do not tell you why. They just give you the answer and they just provide any proof. And even though you follow the proof, you don't know what's going on in there because they are dealing with just a simple number and trick and abstract rules that normal people do not understand at all. But at the end of this lecture, you will find a physical way to understand and to solve the linear equation. Very, very simple way. Another, another way of solving the linear equation is to find out the inverse matrix. It again, if you follow the mathematics, refer to mathematics textbook, there are list of definitions and the definition and new definitions. And it is very difficult for us to keep track on the answer. If you stick to the rule, just like a computer, if you are yourself is AI, then it is very easy to follow. But human brain is not that mathematical, so it is very difficult to follow. Anyway, you can, if you like mathematics, then you can follow this way. You have to keep memorizing everything, but perhaps tomorrow you will forget everything. Just like when you finish the exam, you learn very much, and even you get A plus in mathematics, but in your life you never use them at all, and you forgot how to derive and how to use. That's the problem of mathematics. So equilibrium of two forces. If there are two forces in equilibrium, sum is zero. That means if I move this to the right hand side, you will find that two forces are the same in magnitude, but direction is opposite. Very simple. In addition, equilibrium requires that torque must vanish. So we have two torques, and because the force is in equilibrium, I can substitute this one in here. Instead of F2, I can substitute minus F1. If I, after the substitution, I end up with a single force cross product with the relative displacement of the two objects. I have some force F here, and the other force must be opposite. There's a line between straight line between particle 1 and particle 2. 1 minus 2 is this. Is it possible to have an equilibrium? No, not at all, because center of mass should be somewhere around here, and you have the torque in this way. It's rotating, it is not in equilibrium at all. Then how can I get it an equilibrium? It should be zero. What should I do? Aha, cross product. If force is because force is not vanishing, single force is not vanishing. The cross product vanishes only if this vector is a parallel to F. Aha, that means the force is not in this way. Instead, two particles connected in the straight line, the two forces are aligned. Then it is a perfect equilibrium, as well as the force, as we have equilibrium in the torque. This is complete equilibrium condition for the two forces case. Okay, so we learned this one when we consider the net torque on a system of rigid body or a system of particles. In that case, the total linear moment, total angular momentum inside a system of particles vanishes only if the force between two internal objects are parallel to the line connecting the two particles. That means the central force. The strong requirement of the central force was the one that the internal force does not contribute the total angular momentum of a system of particles. That is the equivalent to this finding. Let us go ahead with the three forces case. If three forces are in equilibrium, the force must cancel. The force must cancel. That means the three sides, they can construct the three sides of triangle. Head and the tail and head are connected in series to construct a triangle. That's fine. So F3 can be expressed as minus F1 and minus F2. What happens to the net torque? That also must vanish. These three torques, I can replace this F3 in here. Then only F1 and F2 dependence survive. In that case, we have this difference. So some of these two must cancel. A little bit complicated, right? In comparison with the three forces case. So anyway, that's the reason why we have to know how to solve the linear equation. That's the problem. I have listed some properties of contact forces. So just to read it through. And this is a simple example how to solve the equilibrium problem. This is typical. We have a stick and two strings that are connected. In here, we have a mass, another mass coming from the stick. Always, we can simplify the system. A rigid body accepts the gravitational force at the center of mass if you solve the problem. That is the simplest case. The center, you have to know the center of mass of a rigid body. The gravitational force is always applied to the center of mass. And we have to find all of the forces applied to this system, and tension is attached in here. And stick, it accepts the force along its own direction. Sometimes it pushes forward. Sometimes and sometimes it has some tension style. But tension does not have a compressive force. It always has a tensile force. That is, from the action point, the force is diverging. Force it does not apply the pressure to the system. For example, this tension cannot make a force of pushing the point A. Okay, the tensile force is like that. And there is a hinge. Hinge has the it's attached to a wall, as an extension of a wall. It applies to a system by a normal force. In addition, hinge can apply a frictional force in either direction that is parallel to the surface. Okay, then what we have to do is first find out the all forces. So find out the net force vanishes. In this problem, we have only two dimensions. It's not a three-dimensional problem. It's just a two-dimensional problem. We have to find the two unit vectors, Cartesian unit vectors, to represent all of the problem. So the force along the E1 and E2, they cancel separately and simultaneously. Net force, there are two forces, and the gravitational force. And this one, hinge applies the system, the normal force and frictional force. And there's a weight. And this weight is identical to this tension. The E1 component of the force can be summarized E1, horizontal force, O T1, and normal force. So T1, there's no pressure. So T1 is applied, for example, at this point, along this direction. This one, and normal force. And there is no other force I can find. Normal force and T1 are identical. And next, we have forces along the vertical direction, E2. F is here, and mg is here, and tension is here. And tension is actually the same as mg. And tension is downward. This is a system, and tension is downward. Small mg is down, and tension is down, mg, capital Mg, F. So we end up with the result, M plus mg is the frictional force. This is the magnitude. The force is upward. What's next? We have to compute the net torque on the system. There are two ways to solve this because torque depends on the point. Because some force is applied, then we have to find the lever arm from the pivot of rotation. So F, X perp, and F is necessary. This is a perpendicular. You don't have to find the X perp exactly. You still have the same torque as long as it's applied to any point along this line. But the answer is only this is an effective one, and the parallel component doesn't contribute at all to the torque. So let us first consider the torque when we choose the reference point to be A. A is the reference point. What happens? Force, this one and this one, does not contribute at all for the torque because there is no lever arm. It is directly connected to point A. So remaining piece is this one. This force has the lever arm, this. This width is W, so it is a half of W. Another force, this normal force applied in here, perpendicular distance, this is H. So N is coupled H. And what is the direction? Direction is clockwise. What is the direction of this force? Again, torque is clockwise. So mg, this one is clockwise, and this force is clockwise, but we have this F force. This one has a width W. W is the lever arm for this force F. Okay, this is rotating counterclockwise. So they make an equilibrium. Okay, the answer is this. What about the case of B as a reference point? If we choose the reference point to be B, then I don't have to worry about these two forces because they do not have any lever arm at all. If I consider this mg is applied to this system, the lever arm will be half of W relative to the pivot passing through the point B. Another force, tension. And this tension is along this direction. Along this direction, we have lever arm H. And this force, lever arm W. That's it. And this force gives the torque along the counterclockwise, this one clockwise, and this one counterclockwise. So counterclockwise, positive sign, and clockwise, negative sign. So that's it. If I combine everything all together, these signs comes from whether it is counterclockwise or clockwise. This one at the end of the day, when we choose the axis to be E3. So, in summary, this one we already obtained, and this one we have already obtained. And in here, we find that this torque vanishes, therefore, N is determined in this equation. So N is determined in here. Because N is determined, N is identical to T1, so T1 is then determined from in here. So fortunately, we didn't have to solve the linear equation. It's automatically solved by choosing a frame of reference, the pivot as a very simple choice. However, in general, it is not easy to find a simple way. This problem is a relatively easy problem. So in that case, we have to put everything all together and let computer to solve the linear equation. But we had better know how can we solve how to solve the equation manually. Only if we can solve in principle, even though we employ computer, we can solve the exact solution, and we have a tool to check whether the answer is correct or not. Computer does not give any correct answer as long as if you do not take care of the program very well, because human error can make the produce a bug in a computer program. So computer is not almighty. Stress, strain, and elasticity. The structure is made of steel, concrete, something like that. Under even in equilibrium, equilibrium does not mean there is no force. There is a big forces and they are in equilibrium. So sometimes it experiences a tensile force that is something like tension. You are in tug of war, then the rope elongates under the force, under the forces applied to the rope by the two teams. There's tensile force. It elongates along the direction of length. In some cases, we put some heavy object on top of body, then there is a strong compression. And on the ground, there is a normal force, and two big forces cancel. However, during the time, this body experiences a very large amount of compression. Then it modifies the shape of the original form. It shrinks the size. There's a compressive stress. And another stress is something like just shearing stress is something like a springboard. You're a diver. If you dive, then you spring on the diving is a board and it becomes a bend. The shape changes perpendicular to the length. This is called the shearing stress. And all kinds of stress applied to an object, it results in strain. Let's see the figure. Stress is force per area, cross-sectional area. The first one is compression stress. Two canceling forces are pressing an object. So relative to the relaxed state, it is being compressed and length is shrunken. That means the delta L is negative, compressive stress. And upon the compressive stress, there is a strain relative to the length, the whole length. There is a change in length that is called the strain. Another stress on a material is tensile force. It is opposite to the compression stress, tensile stress. Again, it is in units of pressure, force per cross-sectional area. Force per cross-sectional area. Hence, under the tensile stress, the length is elongated. So delta L is a positive in this case. So delta L is negative is compression stress, and tensile stress delta L is a positive. Regarding the shearing stress, the length change is not along the length, it is along the perpendicular direction of the length. In any case, the rate of stress and rate of strain, they are similar. They are proportional they are proportional to each other, unless it is completely broken. That is because the elasticity is still working. Sometimes, if the stress is too high, too great, then the material breaks down and it will never return. So, we do not care about such a kind of case. It's dangerous state. The stability should be maintained as long as the stress and strain the relation is proportional to each other. So if you take the ratio, that means stress per strain or stress multiplied by in reciprocal of a strain, inverse, reciprocal, then the product will be invariant. And this is called a modulus. For three cases, we have different name. For compression stress, we use a bulk modulus. And compression strain is negative. So to make this parameter called the bulk modulus to be positive, we have to put the negative sign on this ratio. Again, stress is in units of pressure. Compression strain, negative sign should be there. And we used this special notation B, and this is the bulk modulus relationship because we can multiply the cross-sectional area in numerator, both in numerator and denominator. Then it becomes denominator because volume and becomes the change in volume. Anyway, negative sign should be there for the compression stress strain. Tensile case, everything is the same except that we have removed the negative sign because delta L is a positive. And this ratio for the tensile stress has a special name, Young's modulus. And we use capital E. Shearing stress is perpendicular and it is positive. So we have positive sign. The shear modulus G is defined in such a manner. Ideal flexible string. I have corrected this typo. It is not sting, it is a string. And this problem is, I refer to the Simon's book. And you can find this problem in the section 5.9. And this is a way to solve how to find the bend structure of a wire under gravity. For example, the power line, we have a power line between towers, long wires are bent due to gravity. This is this problem. And you will find that the solution, the shape of this curve, is a linear combination of cosine and sine hyperbolic function. The hyperbolic function you learn in mathematics, but in reality, this one appears this kind of physical problem. And this is due to the gravity of the parts of wire. Or simplified our problem, we do not allow any the elastic behavior, and it is just like connected chain to simplify this problem. And I do not have enough time to explain all of this. And you just, because it is a well solved, and this is not a question and the solved example. So you follow this, and this is a quite good example of solving differential equation. And at the end of the day, you will find that hyperbolic function solves explains the structure of this bended nature of wire under gravity. And the last part will be on solving linear equation by using inverse matrix. As I told you, linear equation can be, before we restrict ourselves to the three-dimensional case first. And linear equations are something like a vector equation. Scalar products, three scalar products are expressed as this kind of form, and combine this one all together. These are common, and the row vectors are written in this form. And this answer gives column vector. And what we want to do is to find out, this is a matrix capital A, and I want to find out inverse matrix. And according to Cramer's rule, the answer is given in here, but here I want to find out the inverse matrix straightforwardly. First of all, these three must be linearly independent to make a non-vanishing volume for the parallel pipe generated by three vectors. I told you these are three vectors. The volume must be non-vanishing. I'd like to make this one as a key point of solving this problem. Let's say, because volume is not vanishing, and we would like to express everything in terms of this volume. So in units of this volume, we use 1 over d, that is the volume's triple scalar product. Factor this volume out in the denominator. And assume we have the solution. I don't know what the solutions are. However, let us claim this and find out the equation that is satisfied by these three columns. Hey, if I know the answer, just substitute it to the equation. Inverse can be multiplied to the left-hand side or right-hand side. Either way, the simplest way is because it is written as a row vector. I'd like to put this one on the right side. And denominator is in here. I multiply capital D, there's a volume of the parallel pipe, both sides. Then, because the answer must be satisfied with the identity matrix, this identity matrix multiplied by D, volume of this parallel pipe, is a DDD. That's fine. What's D? D is A cross B. That's C. Okay. What's this column? This column is to be multiplied in here to find out the volume. What's that? This is A dot alpha vector. And what is alpha? Oh, equals A. This one can be written as a dot B cross C. That's fine. It's always the same. A dot B cross C. The answer is alpha equals B cross C. Everybody knows this. This is B cross C. All right. It doesn't matter. If we multiply this one, what happens? This one, second one is a B dot B cross C. That's a 0. Oh, yes, it is 0. What happens to this? This is a C. C dot B cross C equals 0, 2 because they are parallel. Oh, I have solved this problem. This is B cross C. What happens to this second column? Second column, this is the main feature. Second column is multiplied to B, so B times beta equals D. Oh, what is D? This B dot C cross A. I know the answer. Beta is what? Beta is C cross A. What's next? C cross A, but what happens to the first one? If I multiply C cross A with A, the answer is 0. Right, it's 0. What happens to this? C cross A dot C. C cross A dot C. That's, that's 0. Everything is 0. What happens to this? This is gamma. C dot gamma must be volume. C dot A cross B. The answer is A cross B. And again, A dot A cross B, 0, B dot A cross B, 0. I know the answer. Inverse matrix, B cross C, C cross A cross B. Finally, denominator isn't reproduced. The inverse matrix is this. When A is A vector, B vector, C vector, then this is a row vector. A inverse is B cross C, C cross A cross B, column vectors. That's the physicist solution for the 3 by 3 matrix. This inverse is absolutely simple. You can memorize always. If you do not memorize, just to repeat the calculation. And what I have done is just transforming the division. Inverse is a kind of division. If you're not strong in math, I'm not strong in math, you can convert the division into multiplication. If you're not good at subtraction, why don't you transform it into addition? Then the problem becomes simple. Mathematicians generated a very clever way to find out the solution. The problem is that I cannot remember this complicated formula. I am not clever enough. I'm stupid. However, although I'm stupid, my answer is clever. Everyone can remember this. That's the difference between mathematics and physics way of solving problems. Physics is based on nature, and we have a feeling much better than mathematicians do. Mathematicians are very good, and their IQ is a factor of 5 greater than me. But my way of stupid solving is much better as long as we ordinary people treat the problem. We are not genius. However, we have a way to survive. We do not have to be a mathematician. We follow the physicist way, a practical way to solve mathematical problem. Mathematical problem is always originated from physics problem. If you understand physics, problem solving becomes very, very complex. The answer exists. That's it for today.